Imagine a completely flat, featureless grid representing the Earth's surface. At a single point, we introduce a massive source of localized heat. That surface heat immediately transfers into the resting air molecules. As they warm, they expand, become less dense, and accelerate upward into the atmosphere. By moving vertically, this rising column is physically evacuating mass from the surface. It leaves behind an invisible void, a localized zone of reduced atmospheric pressure. Meteorologists define this surface void as a low-pressure system, or a cyclone. Because the air at the center is now less dense, the surrounding higher-pressure air is physically forced inward by the pressure gradient. This dense surrounding air rushes horizontally to fill the low-pressure void. Notice the exact trajectory of this incoming air. It is moving in perfectly straight lines from high pressure to low pressure. There is zero rotation. A cyclone is defined by this invisible vertical column of rising air, creating a massive surface vacuum. The winds and spin we associate with storms are secondary reactions. We can now shift our focus to a cold zone on the surface to observe the exact mechanical inverse. Here, the upper atmosphere is cold and dense. It tightly packs together and drops vertically toward the ground as a massive, heavy column. As the weight of this subsiding air collides with the surface, it forcefully compresses against the ground. This compression zone creates a high-pressure system, known as an anticyclone. This downward force generates an overpressurized environment at the surface, which causes the newly compressed air to diverge and push outward in a 360-degree radius. Just like the incoming air of our cyclone, these outward-pushing wind vectors initially move in strictly straight lines. The vertical airflow row shows that the mechanical architecture is dictated by whether the central air column is ascending or descending. These opposing vertical engines, rising air creating a surface vacuum and sinking air creating a surface compressor, are the initial drivers of global weather patterns. Now we replace our flat, static grid with a massive three-dimensional sphere rotating from west to east. Because the Earth is spherical, its surface cannot move at a uniform speed. The equator has more physical distance to cover in a 24-hour period, meaning it rotates faster than the poles. This differential in rotational speed generates the Coriolis force. When air moves horizontally across the Earth's surface, this rotation curves its path. The direction of this curve is governed by Ferrel's law, which states that moving objects in the Northern Hemisphere are deflected to their right. Apply Ferrel's law to our cyclone. As heavy air rushes inward, the Earth's rotation bends its trajectory right. This simultaneous turn by all inward vectors locks into a strict anti-clockwise spiral. Conversely, compressed air pushing outward from an anticyclone deflects right, generating a clockwise vortex. The Earth's rotation acts as the primary routing mechanism, locking simple vertical drafts into massive, stable, rotating weather engines. Moving our perspective below the equator reveals the inverse kinematic environment. In the Southern Hemisphere, Ferrel's law flips. All moving air is deflected to its left rather than its right. This leftward deflection mirrors the atmospheric spin. A southern cyclone spins clockwise, and a southern anticyclone spins anti-clockwise. However, there is a kinematic limitation on the exact equator, within a boundary extending 5 degrees north and south. If a low-pressure void forms here, the surrounding air rushes in and fills the vacuum immediately, moving straight inward without any deflection. Because the Coriolis force at the exact equator is zero, tropical cyclone formation along this narrow belt is physically impossible. Without planetary deflection to initiate a horizontal spin, the atmospheric engine stalls. The surface vacuum fills with air instantly, neutralizing the system before a storm can organize. By looking inside the rising vertical column of a rotating low-pressure cyclone, we see how these mechanics produce physical weather. As air is pulled higher, it experiences adiabatic cooling. The lower pressure at high altitudes allows the air mass to expand, forcing its temperature to drop. Cold air has a lower physical capacity to hold water vapor than warm air. As the temperature drops, the ascending air hits a tipping point. The trapped water vapor undergoes rapid condensation, forming thick cloud formations and precipitation. This condensation creates a feedback loop. The change from vapor to liquid releases latent heat into the surrounding air. This newly injected heat warms the column, increasing its buoyancy and accelerating the storm's upward velocity. This document outlines the regional names given to these self-feeding low-pressure engines. Depending on the ocean basin, they manifest as hurricanes, typhoons, or severe tropical cyclones. The destruction associated with a hurricane is the physical byproduct of a low-pressure void aggressively attempting to balance the atmosphere. We return to the descending column of the anticyclone to observe its diametrically opposed effect. As this heavy air sinks toward the surface, it encounters increasing atmospheric pressure that forcefully squeezes the descending column. As a direct result, this intense physical compression actively warms the descending air mass long before it ever reaches the ground. Because warm air can hold more water vapor without condensing, the moisture capacity of this descending column increases. Under these conditions, clouds physically cannot form. Any existing clouds are evaporated by the subsiding dry air, leaving behind completely clear blue skies and calm winds.